Hi everyone, I wanted to make a quick video outlining our work for the QoMEX conference. This is a quick overview of the poster we presented there. The idea is estimating SSIM from MSE for DCT compressed images via local error statistics. So that was the title of our paper we presented. And basically, in 10 seconds, if you want to know, you want to estimate SSIM from the MSE. Now, you can get your MSE from PSNR. So the idea is if you have an encoded frame in either PSNR or MSE, you want to quickly approximate SSIM. And basically, this is what this paper does. We propose this K value, which you compute once, which collapses all the local statistics needed for SSIM into a single scalar that you can apply to your global MSE. So basically the frame level MSE. Motivations, there's a tons of reason why you would want fast SSIM. So any type of highly scaled pipeline where metrics computations are expensive, you might be interested in speeding that up. So there's an appeal to, if I have PSNR or MSE, I can just apply this scalar and get the value for SSIM instead of computing it. So how do we do this? How do we go about this? This was based on earlier work by Martini, and she came up with the following equation here, you can see. And basically, her finding was that you can approximate SSIM using this equation here. And now just for a bit of context, SSIM is computed locally on a sliding window. So basically you would slide the window all over the image, and that would give you a score which you average out, and that gives you the average score for the image. And what Martini showed is that she can approximate the score of these local windows using that local MSE and applying these computations. So you need the variance of that window, and you're able to get a very close approximation of SSIM. Now, the difference here, what's new, is that we actually want to have global MSE. So when you're getting PSNR or MSE, it's going to be frame-wise. It's not going to be block by block. So what we want to do is find a way to go from global MSE to this local version. And the way we do it here is with this equation here. And what it says is that we take the variance of this block as an indicator, and we look at the ratio with the average variance over the entire frame. And basically we distribute the MSE based on how the variance is distributed in that frame. And we have this nonlinear or sublinear component here, which is beta, which allows us to kind of control this. And when we started optimizing for beta, what we noticed was that the value seemed to come often close to 0.5. Now, for those in the know, 0.5 means that this gives you like a square root operation, and square root of variance is actually standard deviation. So we propose a second model, that's parameter free, and which is this version here, which uses standard deviation or the ratio of standard deviation instead of using the variance. All right, so the big takeaway is that if we combine all this together, we can derive a source only, so basically only based on the reference frame, factor called K. So you measure this on K, and for any distortion you get from this image, you just need to get the MSE of that distortion and you can apply it. And by applying it, you'll get the mean SSIM, which is the equation we see here. So it's very interesting because if you're in this case where you're doing this encode or multiple encodes of the same content, maybe different renditions, different bit rates, you can actually save a lot of operations by just reusing this value and getting the either PSNR or MSE directly from your encoder. So we did two different experiments, one on the codec image suite, which is about 24 images, and the second on the XIF dataset subset 1, which is about 50 images, and we tested 4 different approaches. So we can see that the black line here is the ground truth, so that's the real SSIM value. Orange was our baseline, or was this idea, what if we just used the global MSE, so everywhere inside the image. So for every sliding window, we would just use that MSE, and as we can see, that's pretty bad. Blue is prior art, so it's Martini work, which requires the MSE for each sliding window of the image. And we can see our two proposed approaches. So green is the variance version, so the sublinear variance. And then red is the standard deviation version that we proposed. This one's interesting because it doesn't have a parameter. It's a little less precise, but you can see the same thing here. The difference is, in this case, the sublinear variance is tuned to a certain value, and then this one just uses standard deviation, which is pretty close. If you're interested just in seeing how this works, here's a zoomed in version for subset 1. So this is the delta with the SSIM, so the black line is basically 0. We can see prior work by Martini here very close to 0 because it's got all this information for each sliding window. Our approximations here are slightly less precise, but we're talking, these are percentages here. So if you're 1% off, this is just like a 0.01 difference in score for SSIM. So it's still very acceptable, very useful. We see this across a whole range of JPEG quality values, so ranging from 30 all the way to 95. So that's super interesting. We see a wide range of applicability. And then obviously as the range starts to go down and the images are pretty bad, this is where precision starts to drop a bit. So we assume that people tend to go above quality 50 all the way to 95, and in that range the quality is pretty good. So here's all the details of what I just said. This was done on Sidekick SSIM implementation with the default 7x7 windows for SSIM. We saw less than 1% error in like a practical range. We also saw that the curves are monotonic. What that means is that the curves that we showed before, if I go back down, behave in the same way, right? They're not going up and down. It's not a point cloud. It's really this nice curve that keeps going, which means that if you're taking decisions based on this, then these decisions would be very reliable compared to techniques which would have more of a random error onto it. Obviously, like I said before, there is a limit to how this works. So if you're going into these very, very low quality JPEG images, then obviously your scores won't be as precise. But I think at that point, if you're looking at a very low SSIM score, so if you have 0.3 and you're off by 0.05 or something, it's really not that bad because we just know it's bad to begin with. The takeaways we're presenting here, this nice scalar K value, which allows you to go from global MSE to SSIM. We proposed two models, one on variance, the other on standard deviation, and we showed that it works pretty well for the JPEG quality range that most people will use. Here are the references I mentioned when I was presenting this paper, and if you want to try it out, we do have an open source project. You can find it here at approximate on Git. Yeah, thanks for your time. Thank you for watching, and see you in another video.